Last week, we have talked about Capitol Gate Tower's main core construction pre-cambered method and how they stacked up the core. Capitol Gate Tower, the landmark of Abu Dhabi, is the harmonious result of the efforts of designers, structural engineers, and the constructors on site. As we have mentioned previously, Dubai had made the highest building in the world, Burj Khalifa, and an iconic building such as Burj Al Arab. As Dubai did not have any iconic landmark such as these, Sheikh Sultan wanted a building more special than this. He asked for a building not higher or massive than this, but one that could break the common sense of architecture. That is why the designers, inspired by the sand dunes and rolling waves of Abu Dhabi, made the tower as high as it is inclined to one side and tilted as it went up. This was a geographically impossible shape to implement. When the structural engineers received the design proposal, they examined conventional methods to apply to the building and found out it was impossible. So, they needed a unique core and special diagrid to be able to sustain the irregular shape. Until next week, we will explain about the methods applied to the core and how it was constructed. Now, we're going to talk about the unique core they devised. Then why did Capitol Gate Tower need a special core? We have to review the role of the conventional core first. Typically, the core is placed literally at the center of the building. Its role is to sustain the load of each layers of the building and convey only the vertical loads to the foundation beneath. However, as we have mentioned before, in the case of our Capitol Gate Tower, because of the leaning shape, it is impossible for the core to sit at the center of the building. At the base, it sits toward the side of the building that leans out. As the tower climbs around it, the floors gradually stack further and further across the core. Halfway up, the core is at the center of the floor. At the top floor, the core sits against the opposite side of the lean, between the outer wall of the tower and the inside wall of the atrium diagrid. By this, the core gets out of its original symmetrical state. This means that as well as supporting the vertical load of the building, it also has to support the sideways load of the leaning tower, constantly trying to topple the building's upper floors over. Not only that, because of its twisting state of the high building, the floors twist around the core as well as leaning outwards. Therefore, the loads on the final core were extremely complex to figure out. The structural engineers had to set two groundbreaking rules to the core to sustain the building, and these two methods were never applied to other skyscrapers before. The first was using the pre-cambered core method. As we have mentioned last week, the plan was to build the core already leaning to the opposite direction of the lean of the building. After that, as constructors added the slabs to the upper levels, the weight of the leaning parts would pull the core back into a vertically straight state. The whole core would be in tension, and that gives it immense strength. However, this pre-cambered concrete core wasn't enough to sustain the lean. There was the risk of cracks generating due to the overhang, and steel rebars couldn't help this problem. The engineers struggled to think of another solution. This is where the second groundbreaking method enters the stage. It was using post-tensioned tendons. This is a method of reinforcing concrete that involves compressing the concrete after it is set by tightening long screws and tendons that run vertically through it. Vertical post-tensioning is common in certain types of civil engineering structures, such as bridge piers and containment structures, where lateral loads tend to be more significant, says Brooks of Gifford. The compression from the tightening bolt reduces tensile strength in the concrete, caused by the lateral loads pulling them sideways, which concrete is not good at resisting alone. Capitol Gate is the first tall building to use vertical post tensioning in the core because the loads it has to withstand, both as it was built and once it was complete, were so untypical. When the tendons are stretched, the stress counteracts the pulling force created by the massive overhang, stopping the concrete from tearing apart. First thing to consider more than else was to realize the leaning design. They had to construct gradually biased slabs and the pre-cambered core that could sustain this, and this had to be progressed at the same time. However, Capitol Gate Tower wasn't tilted from the start. From the ground floor to level 13, it goes straight up. So, in the initial construction process, they had to consider making the core and slab and connecting them together. However, in the lower levels, the core was placed at the edge of the slabs, which made it impossible to sustain it alone. That is why they needed to sequentially make the core, diagrid, and slab mold, and then put them all together to create one floor. To link the slab and core, they put in rebars to stop the overhang of the tilted slabs. But as the tower rised and the floors were added, the core's mold was placed at the opposite direction of the lean. The slab's mold moved to the direction of the lean to realize the form of the lean shape. After that, as the floors went up, the building needed to be able to sustain the increasing overhang. So, they started to construct the 20 meters tendons and gave tension to them. Before placing the tendons inside the core, they were given post-tension on site. When the concrete core came up to an appropriate height, the long tendon was lifted to the top of the core. As the tendons were 20 meters long, heavy, and were bended irregularly, it was impossible to pick up the end point of the tendon and place the opposite point exactly to the duct with handwork. That is why in this process, it was necessary to bring in the crane to the construction site. Then how did the tendon get in? The team used the steel tendon's weight to force it through a duct already cast through the core. Once the tendon got in position, the team would lock off both ends, ready to tension its individual strands once again. This was when the FEM analysis came to light. The FEM analysis helped the Gifford team to determine at which point in its construction the building would begin to pull hard enough on its core and start deforming it. This helped to define aspects of the construction process, such as how far the core construction had to be ahead of the floors and what point the post-tensioning had to be added. As our Capitol Gate Tower had an uneven loading in each layer, the tension needed in each part of the core had to be different. From their calculation, the appropriate tensile strength required was 6 megapascals at foundation level to level 18, 8 megapascals from level 18 to level 27, and 4 megapascals from level 27 to the roof. A pneumatic jack clamps around the tendon one strand at a time and stretches it to the right stress level, and then concrete pouring can continue upward, and this process repeats. This is how post-tension tendons were used. From these sequences, we were able to get one step closer to realizing the tilted design. This week, we have explained the methods used to solve problems caused by the tilt of the Capitol Gate Tower in relation to the core. However, except for the tilted problem, the process still required additional solutions to other problems. Therefore, we will explain the problems and solutions that occurred in height and temperature when building next week.